Imagine waking up one morning to find that the invisible climate engine keeping your entire world warm and stable has suddenly broken down. Deep in the dark depths of the Atlantic Ocean, a giant current that moves more water than every river on Earth combined is losing its speed and power right now. This massive ocean river has shaped human civilization for thousands of years by carrying tropical heat from the equator all the way up to the icy northern poles, but modern scientific instruments show that this vital ocean heartbeat is slowing to a dangerous crawl, threatening to unleash sudden freezing winters across Western Europe, violent heat waves near the equator, and rapid sea level spikes along major coastal cities. If you love uncovering the deepest real secrets of our planet without any clickbait or exaggerated drama, please hit that subscribe button right away. By joining our growing community today, you will always be among the very first to discover how Earth's hidden systems truly work and what these dramatic shifts mean for our shared future. To truly understand what is happening in the Atlantic Ocean today, we first need to look at how our planet manages its heat across thousands of miles. The sun shines directly on the middle of Earth near the equator, heating the air and ocean water to very high temperatures throughout the entire year. Meanwhile, the regions near the North Pole and South Pole receive far less direct sunlight, making them extremely cold and covered in massive sheets of ice. Without a way to share this energy around, the equator would become a burning desert where nothing could survive and the poles would freeze into completely lifeless, icy wildernesses. Thankfully, Earth has a built-in heating and cooling system that continuously balances these temperatures to keep life comfortable and safe across the globe. This system is driven by giant ocean currents that form a connected global loop, often called the ocean conveyor belt. Warm water sitting near the surface acts like a massive moving highway, carrying solar heat away from the tropics and pushing it northward toward cooler countries. This flowing warm water gives off its stored heat into the cold atmosphere, keeping places like the United Kingdom, Scandinavia, and Western Europe much warmer and milder than they should be based on their geography. For a very long time, scientists and historians believed that this ocean conveyor belt was an unstoppable force of nature that could never be broken or turned off. People assumed that because the Atlantic Ocean is so vast and holds millions of cubic miles of salt water, surface weather changes could never interrupt the deep flow underneath. School textbooks taught generations of students that ocean currents were permanent fixtures of our world that would remain steady for millions of years. Cities were built, farms were planted, and entire global trade routes were created on the assumption that spring, summer, fall, and winter would always arrive right on time. However, when modern oceanographers began placing deepwater sensors, floating robotic probes, and satellite tracking systems throughout the Atlantic Ocean, that old confidence shattered completely. The ocean conveyor belt was not an indestructible machine made of iron. Instead, it was a finely tuned natural engine powered by subtle differences in water temperature and saltiness. These scientific measurements revealed that small changes in the chemical balance of the ocean could easily throw the entire global current out of order. The entire mechanism relies on a simple yet powerful physical process that acts as a natural pump deep inside the North Atlantic Ocean. Warm ocean water traveling northward from the equator carries high amounts of dissolved salt, which makes it dense and heavy compared to plain water. As this warm, salty current approaches the freezing air near Greenland, Iceland, and Norway, it releases its stored heat into the sky and cools down rapidly. Because cold water contracts and becomes much heavier than warm water, this freezing, salty seawater gets extremely heavy and begins sinking miles down toward the dark ocean floor. When millions of tons of this heavy cold water sink near Greenland, it creates a powerful underwater suction effect at the ocean surface. This suction pulls new warm water up from the tropical south to fill the empty space left behind, keeping the conveyor belt running smoothly without stopping. And the cold water that dropped to the bottom then crawls slowly back south along the ocean seabed, completing a massive circular loop that spans thousands of miles. Scientists give this specific Atlantic Ocean loop a technical name, the Atlantic Meridional Overturning Circulation, or AMOC for short. Have you ever stopped to think about how much water actually flows through this deep ocean conveyor belt every single second of the day? To give you an idea of its incredible size, it moves more than 20 million cubic meters of water per second, so leave a comment down below guessing how that compares to your local river, and tap that like button if you want to support real scientific education. For thousands of years of human history, this ocean pump operated so smoothly that people barely paid attention to its existence. Western European nations enjoyed comfortable summers, soft rains, and mild winters specifically because this ocean loop delivered a massive amount of tropical heat directly to their doorsteps every day. Major cities like London and Paris sit at the exact same northern line on the map as freezing parts of Canada, yet European cities enjoy far milder winters precisely because of this oceanic heat delivery. In the past, major climate models predicted that even if global air temperatures rose slightly, the ocean current would simply adjust and continue running normally. Scientists believed that the sheer volume of the Atlantic Ocean would easily absorb surface changes without causing any sudden interruptions to global climate patterns. The general consensus was that any major slowdown or collapse of the current would take thousands of years, placing it so far in the future that no human alive today would ever need to worry about it. However, when researchers began analyzing ancient mud from the seabed and drilling ice cores deep inside the Greenland ice sheet, they made a shocking discovery about Earth's history. In the distant past, this exact ocean conveyor belt had slowed down and shut off suddenly, causing dramatic climate shifts in just a matter of years rather than centuries. Instead of changing slowly like a smooth ramp, the ocean current behaved like a light switch that could suddenly flip from on to off without much warning. The difference between what scientists originally expected and what they actually found in the historical record matters immensely for everyone living today. Modern human society, including our global food supply and water infrastructure, is built entirely on the idea that climate will remain consistent and predictable. We plant wheat, corn, and rice during specific months because we count on rain and sunlight arriving at precise times each year. If the ocean light switch flips off, the stable environmental foundation that supports modern agriculture will change almost overnight. To make matters far more urgent, fresh water has been pouring into the North Atlantic Ocean at an unprecedented rate over recent decades. The massive ice sheet sitting on top of Greenland holds enough frozen water to raise global sea levels by 20 feet if it were to melt completely. As global air temperatures rise, that ancient polar ice is melting faster than ever before, sending trillions of gallons of pure, non-salty fresh water pouring directly into the ocean where the conveyor belt usually sinks. This sudden rush of fresh water creates a major physical problem for the ocean pump that most people never consider. Fresh water from melting glaciers does not contain dissolved salt, which means it is much lighter and less dense than normal seawater. When this massive blanket of light fresh water spreads across the surface of the subpolar ocean, it floats on top of the heavier salty water like a layer of oil sitting on water. The warm, salty water coming up from the equator can no longer get heavy enough to sink through this freshwater cap. Without that deep sinking action near Greenland, the powerful suction force that pulls warm water northward disappears entirely. Think of it like putting a solid plug inside a household drainage pipe. If the water at the bottom cannot drain out, new water cannot flow into the pipe from the top. As a result, the entire Atlantic conveyor belt begins to stall, leaving heat trapped in the southern oceans while leaving the North Atlantic shivering in the cold. Here's a striking detail that left scientists completely stunned when they first examined high-resolution satellite temperature maps of the world. While almost every single region on Earth has experienced significant warming over the last 50 years, there is one famous patch of ocean that has actually gotten colder. Sitting directly below Greenland in the subpolar North Atlantic is a strange horseshoe-shaped region of ocean known as the cold blob. This persistent spot of freezing surface water is direct physical proof that warm water is no longer making its full journey north. Did you know that a single cold spot in the middle of the ocean can completely change wind direction and storm paths across North America and Europe? Comment your thoughts below on how connected our global weather really is, and hit that subscribe button if you are enjoying this breakdown of deep Earth science. When marine scientists realized that the Atlantic conveyor belt was showing real signs of weakness, they teamed up to build a network of deep-sea monitoring stations across the Atlantic Ocean. One of the most famous projects is called the Rapid Monitoring Array, which uses heavy steel cables stretched across the seabed at 26 degrees north latitude to track ocean movement. These instruments measure water temperature, salt levels, and current speeds at every ocean depth continuously, 24 hours a day. The raw data collected by these oceanic sensors confirmed what many climate researchers feared. The Atlantic conveyor belt is currently operating at its weakest point in over 1,600 years. Since the middle of the 20th century, the overall strength and speed of this ocean current system has dropped by roughly 15%. While a 15% drop might sound small on paper in terms of global heat transport, it represents a massive reduction in the energy moving through our planet's climate system. Historically, most computer simulations suggested that even if the ocean current weakened, a total shutoff or collapse would be virtually impossible within our lifetimes. Official reports published by major global scientific panels stated with medium confidence that the ocean loop would remain stable through the end of the 21st century. Most experts argued that while the current might slow down slightly, it would remain strong enough to prevent a catastrophic climate shift. Yet, a landmark scientific study published by researchers at the University of Copenhagen completely overturned those cautious predictions. By applying advanced mathematical analysis to sea surface temperature records going back to the year 1850, they looked for early warning indicators that signal when a natural system is losing its stability. They were tracking a mathematical concept known as critical slowing down, which occurs when a complex system takes longer and longer to recover from small environmental disturbances. What these scientists uncovered created shock waves throughout the global meteorological community. The mathematical data clearly showed that the Atlantic Ocean loop is losing its resilience and heading directly toward an environmental tipping point far faster than anyone previously calculated. According to their statistical models, the current could experience a complete and irreversible collapse much sooner than expected, potentially occurring within the coming decades of this century. This massive gap between older models and new scientific findings matters because a collapse in our lifetime changes how we must prepare for the future. If the Atlantic Ocean motor stops within a few decades instead of several centuries, millions of families alive right now will witness a totally transformed planet. It shifts climate change from a distant problem for future generations into an immediate operational challenge for towns, cities, and nations right now. Pay very close attention to what happens if this deep ocean current slows down even further, because the weather consequences will be dramatic and widespread. If the warm ocean river stops delivering tropical heat northward, Western Europe will not experience warming like the rest of the planet. Instead, it will suffer a severe cooling trend. Average winter temperatures across countries like Great Britain, France, and Germany could drop by 5 to 10 degrees Celsius in a remarkably short period. To help you picture what a 10 degrees Celsius drop actually means in everyday life, it would make winters in London and Paris feel like modern winters in northern Canada or Scandinavia. Snow would cover farmland for months at a time, local crop growing seasons would shrink dramatically, and home heating needs would skyrocket across entire nations. European agriculture would face unprecedented crop failures as traditional crops like wheat and barley struggle to survive in the sudden bitter cold. At the exact same time Western Europe is freezing, heat will get trapped near the equator and across the southern hemisphere. Because the ocean conveyor belt can no longer carry tropical heat northward, the waters around Central America, West Africa, and the Caribbean will become dangerously hot. This intense heat accumulation near the equator will power unpredictable weather events, supercharging tropical hurricanes and completely altering global trade winds. Can you imagine living in a world where northern countries face bitter sub-zero cold while tropical regions experience dangerous heat spikes simultaneously? Drop a comment below sharing how weather patterns have been changing in your hometown, and share this video with anyone who enjoys learning about planetary shifts. The dramatic shift in ocean temperatures will also force a major movement of the tropical rain belt, which is a global band of heavy rainfall that feeds billions of people. Normally, this rain belt stays locked near the equator where warm, moist air rises into the atmosphere. But as the subpolar Atlantic cools down and the southern oceans heat up, the entire rain belt will be pulled southward away from its historical position. This movement will disrupt the life-giving monsoon rains across West Africa, India, and Southeast Asia, which millions of farmers rely on to water their crops every single year. When monsoons arrive late or miss their target regions entirely, widespread droughts occur, destroying essential harvests of rice, millet, and corn. Regions that have relied on predictable summer rains for thousands of years could face severe water shortages, while other areas suffer from sudden catastrophic flooding. Meanwhile, along the eastern coastline of the United States, a slowing Atlantic conveyor belt creates a totally different kind of danger for coastal communities. As the northward current slows down, water begins to pile up against the American East Coast instead of being pulled rapidly away toward Europe. This piling effect can cause sea levels along major cities like New York, Norfolk, and Miami to rise by several additional inches on top of normal global sea level rise. An extra increase in local sea level means that routine high tides will flood urban streets, push salt water into freshwater drinking wells, and cause severe damage during winter storms. Coastal storm surges will penetrate much deeper inland, damaging homes, roads, and power stations that were never designed to withstand such high water levels. A slower ocean current effectively turns ordinary coastal storms into major financial and humanitarian disasters for millions of people. What marine geologists discovered when studying ancient ocean floors revealed an even deeper connection across our entire planet. The Atlantic conveyor belt does not operate in isolation. It is intricately linked to ocean currents in the Pacific, Indian, and Antarctic Oceans through a giant global network. A major breakdown in the Atlantic triggers chain reactions that ripple across every ocean basin on Earth, changing rainfall, wind patterns, and sea life worldwide. For example, warm water conditions in the Indian Ocean can alter atmospheric winds in ways that push additional salty water back into the Atlantic Ocean. While these complex oceanic feedback loops can sometimes slow down the rate of decline, they also create unpredictable weather wildcards that supercomputers struggle to forecast accurately. The world's ocean system acts like a delicate web. When you pull hard on one string in the Atlantic, every single ocean strand feels the strain. In past decades, many policy experts assumed that if humanity managed to lower global air temperatures in the future, the ocean current would simply start back up like a restarted car engine. They believed that environmental recovery was a smooth two-way street where fixing atmospheric temperatures would automatically restore historic ocean flows. However, advanced computer simulations of fluid dynamics reveal that the ocean conveyor belt suffers from a physical property known as hysteresis. This means that once the current crosses a critical threshold and shuts off completely, it requires far more environmental effort to turn it back on than it took to break it. And even if air temperatures return to normal levels, the ocean loop could remain stuck in its collapsed state for hundreds or even thousands of years. Is it mind-blowing to realize that a broken ocean current could stay turned off for hundreds of years even if human society fixes global temperatures? Let us know what you think in the comments section, and click that like button to help spread real Earth science to more viewers around the world. This long-lasting lockout happens because the freshwater cap floating on the North Atlantic creates a self-reinforcing environmental loop. Once the deep sinking process stops entirely, warm, salty water can no longer flow northward to flush out that freshwater layer. The cold, fresh water stays glued to the surface like a heavy blanket, keeping the ocean pump permanently locked in the off position regardless of weather changes above. Because the potential consequences are so severe, a coalition of over 40 top international oceanographers and climate scientists issued an urgent open letter to global leaders. They warned that the risk of a total collapse in the Atlantic conveyor belt has been severely underestimated in standard international policy planning. They urged governments to take this oceanic tipping point seriously, emphasizing that adapting to a collapsed ocean current would be nearly impossible for many nations. Right now, scientists are closely monitoring real-time data streaming from research ships, deep-sea buoys, and orbital satellites stationed across the North Atlantic. They are tracking salinity levels, measuring surface currents, and calculating the exact speed of deep underwater flows every single day. Every new batch of ocean data brings us a clearer picture of how fast this massive natural engine is changing right beneath the ocean waves. It can be easy to look at the ocean and assume that deep underwater currents have little to do with our daily routines on land, but the food available in your local market, the cost of your heating bill, the safety of your home, and the weather outside your door are all directly tied to this ocean heart. The air we breathe and the rainfall that nourishes our crops are shaped by how heat moves across the surface of our planet. To see how fragile this system really is, we can look back at an event that took place roughly 12,800 years ago, known to scientists as the Younger Dryas. During this period, a colossal freshwater lake in North America formed by melting ice age glaciers suddenly burst through its natural dams. Trillions of tons of icy fresh water rushed out through the St. Lawrence River straight into the North Atlantic Ocean in a matter of weeks. That sudden freshwater flood dumped so much light water into the ocean surface that the Atlantic conveyor belt shut down almost instantly. The temperature across the northern hemisphere plummeted by several degrees in less than a decade, throwing human populations and ancient animals into a sudden mini ice age that lasted for over 1,000 years. Archaeologists have found that ancient human tribes had to completely change their hunting habits and migration routes just to survive the sudden bitter cold. The Younger Dryas proves beyond any doubt that our planet's climate does not always change in slow, gentle curves over millions of years. It shows that when critical ocean tipping points are crossed, environmental shifts happen with terrifying speed and intensity. Understanding this ancient event helps us realize that the ocean systems we depend on today have failed before, and they can fail again if the balance of salt and temperature is disrupted. When we examine how modern cities are built today, we realize how vulnerable our global infrastructure really is to sudden climate changes. Millions of miles of roads, electrical grids, water pipes, and railway tracks were built with the assumption that local temperatures would stay within a very narrow historical range. If a region that usually experiences mild winters suddenly suffers months of deep Arctic freeze, roads crack, power lines collapse under heavy ice, and water pipes burst under the extreme pressure. Furthermore, consider the massive impact on global shipping routes and supply chains that carry food and manufactured goods across the planet. If the North Atlantic experiences severe, unpredictable weather shifts, storm tracks will become far more intense and chaotic, making ocean transport far more dangerous and expensive. Freight ships would face massive waves, icy conditions, and unpredictable gales, causing long delays for critical goods, medicines, and food shipments around the world. The financial cost of adapting to a collapsed ocean current would be astronomically high for almost every nation on Earth. Coastal communities would have to spend billions of dollars constructing massive seawalls to block rising ocean waters caused by the piling effect of stalled currents. At the same time, governments in northern countries would need to spend vast fortunes upgrading heating infrastructure and insulating buildings to protect citizens from Arctic winters. In agricultural regions, farmers would be forced to abandon crops that their families have grown for generations in favor of cold-hardy plants that can survive short, chilly growing seasons. However, switching crops is not a simple process. It requires new equipment, different fertilizers, and entirely new supply networks to get food from fields to city markets. During the transition period, global food prices would spike dramatically, creating severe economic pressure for millions of lower-income families. We also have to look at what happens to marine ecosystems and ocean life when these massive currents slow down and change direction. The Atlantic conveyor belt does not just move heat around the planet, it also transports essential nutrients like nitrogen and phosphorus from the deep ocean floor up to the surface. Tiny ocean plants known as phytoplankton rely on these deep nutrients to grow, forming the absolute foundation of the entire ocean food web. When the deep ocean sinking action stalls, the upward movement of these vital nutrients slows down significantly across thousands of square miles of ocean. Without a steady supply of nutrients, phytoplankton populations collapse, which directly harms fish populations, seabirds, whales, and commercial fishing fleets. Entire fishing industries that feed millions of people and support local coastal economies could see their harvest shrink to a tiny fraction of historical levels. Additionally, marine animals that migrate thousands of miles across the ocean rely on ocean currents to navigate and conserve energy during their long journeys. Sea turtles, salmon, eels, and many species of sharks use the predictable flow of ocean currents like underwater highways to travel between feeding grounds and breeding areas. If these highways change speed or vanish entirely, these animals become disoriented, leading to sharp declines in wildlife populations across the globe. It is equally important to think about the psychological impact that major climate shifts have on communities and society as a whole. When the natural rhythms of nature that people have counted on for generations suddenly change, it creates widespread anxiety and uncertainty about the future. Farmers lose confidence in their planting schedules, city planners struggle to design safe buildings, and families worry about whether their homes will remain safe from extreme weather. However, learning about these complex planetary systems gives human society a unique opportunity to take meaningful action before critical tipping points are passed. By understanding the exact physics of how fresh water, salt levels, and heat interact in the ocean, scientists can build far more accurate early warning systems. These ocean monitoring networks allow us to track changes in real time, giving city planners, farmers, and leaders crucial time to prepare and adapt. Every single measurement taken by ocean buoys, every satellite pass overhead, and every ocean floor sample analyzed by geologists adds another piece to this complex global puzzle. Science gives us the power to see around the corner, transforming what would be a sudden catastrophe into a challenge that we can plan for and manage with intelligence. The more we invest in ocean research and environmental monitoring, the better equipped we will be to protect our shared home. When we zoom out and look at the long history of Earth, we realize that human society built its cities and farms during a remarkably stable climate period. For the past 10,000 years, predictable seasons permitted humans to invent agriculture, build thriving cities, and establish interconnected global markets. Studying these deep ocean currents is not about creating panic, it is about respecting and understanding the natural systems that keep our planet habitable. Every new fact we discover about the ocean gives us a better opportunity to plan, adapt, and protect our communities for the future. The better we understand how Earth's ocean currents interact, the better prepared we will be to safeguard our food supplies, protect coastal towns, and care for the natural world we depend on. If you enjoyed this deep, factual look into Earth's changing ocean systems, please hit that subscribe button right now and turn on all notifications so you never miss our upcoming science stories. Leave a comment below answering this question. How do you think our societies should prepare for potential major weather shifts in the coming decades? Please share this video with a friend or family member who loves exploring real Earth mysteries, as your support helps us bring more deep, factual content to viewers everywhere. Thank you so much for watching today. Stay curious about the world around you, and we will see you in the very next video.